Good afternoon, everyone. I'm really sorry for the delay. Actually, there was a issue with this screen recording. That's why it took me a little bit of time. I hope you all are doing well. So today is the week second of this live sessions. I am Danish Bashir, your TA for Structural Analysis 1. So I hope you all are going through the videos that are continuously posted online on NPTEL website. So in those, I think from last 2 weeks, these topics would have been already covered. Loads on structures and computation of the calculation of support reactions and other stress resultants. So regarding these two topics, I will be giving today brief overview, and we will be solving some numerical problems. And this session will be completely focusing on focusing on solving numerical problems. But I think a little bit of introduction is also necessary so that you people will be comfortable in solving numericals. Let's start today's session. Is what are the loads on the structure? Okay. So Starting with loads on a structure. So what is the objective? First, we will see the objective. Objective of a structural engineer is to design a structure that will be able to withstand all the loads to which it is subjected while serving its intended purpose throughout its intended lifespan. So the structure is required to serve its purpose for the time it's being made. Okay, so first we have to calculate all the loads, what loads act on a structure, and then analyze the structure, and that analysis is then being used for post processing like designing of members and other things. Depending on that, loads are usually categorized into three different categories, broad three different categories. One is dead load, another is live load, and third one can be, we can categorize it into environmental loads. So dead loads are only those loads which are because of the self weight of a structure or a structural system and other materials that are permanently attached to a structure. For example, we have a building like this. So all the members, structural members of this building, the self weight of these structural members constitute the dead load of this structure. Be it either be beams, it be columns, or it be floor systems. Okay, all these structures, the self weight of these structures constitute the dead load. All the other things, other maybe non-structural members, like we have other things attached to our building, but those things should be permanently attached to it. The self weight of those things also constitute to the dead load of a structure. So there are different codes in IS, and we have different IS codes that give us the dead loads of different structures. For example, we can see here is the we can see if our building is made up of brick walls here. So for brick walls, the unit weight we have to take as dead load is 18.8 kilonewton per meter cube. Okay. For example, concrete, either reinforced concrete, it will be 23.6 kilonewton per meter cube, or structural steel. For that, we have to take 77.0 kilonewton per meter cube. And for wood, it's very less because wood is not that dense. It's 6.3 kilonewton per meter cube. Then the other category of the loads is the live loads. Live loads are those loads which are movable or moving loads due to the use of the structure. For example, we have a bridge. On bridge, we have vehicles going to and fro all the time. So those vehicles plus pedestrians also. So those the loads that these vehicles and pedestrians impart on our bridge can be categorized in live loads. There are other loads which come into live loads, but there is a further category known as environmental loads, such as wind load, or this snow load. These are live loads, but these are categorized into other category, that is environmental loads, because it is because of the environmental effects around a structure that these loads get imparted on our structure, like wind load, snow load, and earthquake load. So it was a basic thing about the loads. For live loads, we also have different values that we can use in our analysis as well as design processes. Like for hospital, patient rooms, residential dwellings, apartments, hostel guest rooms, school classrooms, we have to take a live load, average live load of 1.92 kilopascal. Okay. For library, reading rooms, and laboratories, we have to use 2.87 kilopascal. Okay. So usually in structure analysis, we use kilonewton per meter square. Okay. So it's given in kilopascal. We can easily convert it into that form. Another category can be dance halls, restaurants, gymnasiums. We can take for that 4.79 kilonewton per meter, kilopascal. Then we have, I already told you these come under environmental loads. Okay. Environmental loads. All these come under environmental loads. These things. Wind loads, snow loads, earthquake loads, these are all environmental loads. Then another type of load can be impact. Impact loads are, for example, impact loads can be, for example, there is a blast in any building or something very heavy stuck on a building. Those loads can be categorized into impact loads, and their analysis comes in dynamics, not in the statics. So this is a static analysis of structure. So their analysis comes in the dynamics of structures. So impact loads are very dangerous for our structure. And then our wind loads, I already discussed these. Coming to our next thing is we have analysis of structurally determinate structures. So now we come to the analysis to determine the support reactions and to determine the stress resultants. As in the first lecture, I already told you what is the objective of this course is we have to determine support reactions and we have to determine the stress resultants, either shear forces or moments that get generated in our structure because of the external loads. So for that, we have to first discuss some of the basic concepts like the equilibrium of the structure. So when we can say that structure is in equilibrium. So the conventional definition for that is a structure can be considered in equilibrium if initially at rest, it remains at rest when subject to a system of forces and couples. For example, uh, it's a beam, simply supported beam. We have like this. We applied some concentrated loads to our structure P1, P2, P3. So initially this structure was not loaded, it was unloaded structure. So after loading the structure with P1, P2, P3, if it's again able to maintain the equilibrium, then can say that this structure is in equilibrium. So what is the prerequisite for the equilibrium of the structures is that that structure should follow both the things, that is force equilibrium as well as moment equilibrium. I'm considering it in a 3D space. A structure is in 3D space. Here I draw it in only 2D. So if it's a 3D structure, like different forces are acting in different directions, F1, F2, F3, and moments are also acting M1, M2, F4. So along all the three respective coordinate directions, X, Y, and Z, both force equilibrium as well as moment equilibrium should be satisfied. So we have three coordinate directions, and along each coordinate direction we have two equilibrium equations. One is force equation, force equilibrium equation. Okay, another one is moment equilibrium equation. Okay, moment equilibrium equation. So we have two. So total number of equations we got is 3 multiplied by 2 is 6 equations. 6 equations for 3D problems. So, but 3D problems are very rare in this course because those 3D problems you can easily do the structural analysis when you know about 1D and 2D. 3D is just an extension of 2D. So basically, in this structural analysis course, most of the problems you will be dealing will be 2D problems. So, for example, here I have shown a 2D body on which different forces F1, F2, F3, and F4 are acting, and along with this, moments M1, M2, and M3. Some books also wrote moments at couples. These couples are acting as M1, M2, M3 on this body. So there are only two coordinate axes, X and Y, and there is no Z axis. So for example, we have two directions. We can have only two force equilibrium equations, Fx and Fy. And these Fx and Fy will be able to create moments along only one perpendicular direction, and to both of these Fx and Fy, mz is perpendicular to this plane. So these Fx and Fy forces will be creating moment mz. That's why there is only one moment equilibrium equation, that is mz. So there will be only three equilibrium equations. equations in a 2D problem. You have to remember it throughout this course because it's very important. After this, coming to other things is, and one more thing is, if there is a concurrent force system, for example, concurrent force system is a, for example, if it's a circular body, something like this, it's having center like this. It is being acted upon different forces like F1, F2, F3. It's clear that F1, F2, F3 all three are having different directions. But what is common is that they are passing through a same point. Okay. So for this type, with these type of force systems, we only need to satisfy Fx summation of Fx should be equal to zero. Summation of sorry, summation of Fy is equal to zero. Okay. These two things we need to satisfy for concurrent systems because summation of m z is equal to 0 is already satisfied because of this property that these all forces are passing through a single point. Okay, so this was a small tip. Now there is another category on this categorization of the forces that act on a structure. These can be external forces and internal forces. So external forces are those forces or actions which are imparted on our structure because of the actions of the other bodies. For the convenience of the analysis, we further categorize these external forces as applied forces, usually referred to as loads. For example, the loads acting on our structure, and another category is reaction forces. So reaction forces are actually the reactions developed at the supports. These are external forces. Another thing is internal forces. Internal forces are the forces and couples exerted on a member or a portion of structure by the rest of the structure. Now, another basic concept, very small concept, is static determinacy and interdeterminacy, and what is the degree of indeterminacy in a structure. So, a little bit about that, then we will proceed to our numerical problems. So, what is internal stability? How we can say that a structure is internally stable, externally stable? What are all these concepts? I will give a brief overview about this. Is a structure is considered to be an internally stable or rigid if it maintains its shapes and remains a rigid body when detached from its supports. For example, I have a I have a truss like this. Okay, so all are hinges. You know that I in last class I give you the definition of a truss, how the force transmission truss occurs, and what is the basic property of truss. And for example, I have a truss member like this. For example, if I remove it from its supports, so I will be left with this. I'll be left with this structure only. Okay. I will be left with this thing. So if you see after removing the supports, if this structure is able to maintain its stability, it's not getting distorted or anything like that is happening, then we can say that this structure is an internally stable structure. So these all are hinged. For example, if I had another type of structure, this was one member of a truss, this was another member of a truss. Okay, there was a hinge like this here. So it was supported like this here, and there was another roller. So if I try to remove it from, for example, I will show it another page. If I try to remove it from its support reactions, for example, these supports I will remove. Then the structure I'm left with is this thing and this thing. Okay. So this thing, you know it's a hinge. So because of this member, moment will be developed, and it will this hinge is not able to resist the moment. It will fall down like this. It will fall like this. Okay. So you look when I removed the support reactions or the support when I removed the supports from this structure, it was not able to maintain its stability. So this is not a internally stable structure. Maintain shape. One more important thing is about the types of supports and how many reactions for each supports are there. Reaction full. So there are three categories for this thing. Support reactions. We have category one. We have category one. We have category two. We have category three. Okay. So in category one, we have three types of supports. One is roller support, another is rocker support, and third one is link. So here, roller support is usually shown by this figure. Okay, so and mainly you have seen roller support like this. So this is a beam. For example, if this is a beam section, so usually we show roller like this. We show roller like this. Okay, roller support. So in roller support there is only one reaction. It can give reaction from here. Okay, so from this direction it's free, no reaction. So from there is no reaction. There is only one vertical reaction. So this roller support may be inclined somewhere like this. There is an inclination given. So a reaction will be perpendicular to the inclined plane. Okay, look here. Another type is a rocker support. Rocker is like this. It can move on happening. Rocker here is again only one this reaction. Then another type is a link. In a link, there is also only one reaction, and it is directed along the link direction. Okay. Hinge we have two types of two reactions only. So we can have Rx and we have Ry. Okay. One support reaction, one actual reaction. Okay. Another is a fixed commonly studied joint is. So we have a fixed beam. Fixed support like one function, one axial Rx, one vertical Ry, and a moment is also developed like this. Okay, MZ. I usually already showed it. So based on this thing, there is another classification, determinate structure and indeterminate structure. I already told you we are dealing with 2D structures only. So number of equilibrium equations that we can maximum write is three equations. Okay, equation. So on this concept, there is one more classification, that is determinate structure and indeterminate structure. When we will call a structure determinate is um, a structure is statically determinate if all its support reactions can be determined by solving equilibrium equations of equilibrium. Okay. So whatever the from unknowns, I meant to say that its support reactions, if all its support reactions can be computed using the four equations of the equilibrium, then it's a statically determinate structure. For example, in figure here, it's shown that a cantilever beam. Cantilever beam. If you draw the free body diagram at a fixed support, you will have Rx reaction. You have sorry, it's not Rx, it's Ry. You have Ry reaction, you have Rx reaction, and there is a moment Mz also. There is a moment Mz also. So, and we know that for this 2D structure, we can write three equations. That is summation fx is equal to 0, summation fy is equal to 0, and mz is equal to 0. Summation mz equal to 0. So number of unknowns is 3, number of reactions is 3. So this all the three unknowns can be computed using three equations. So three equations. So three unknowns and three equations. So we can call this structure as statically determinate structure. Another can be here simply supported beam. In simply supported beam, we again have at roller support we have only one reaction. At hinge we have two, one vertical and one axial. So total number of uh, reactions is three, and equations is three. So it's statically determinate structure. Here in this portal frame also we have roller support and we have hinge support. On hinge we can there can be only two reactions developed. This one lateral and one vertical. So here on roller there will be only one vertical. So total number of reactions is equal to 3, and total number of equations we can write for this 2D structure is 3. So again it's a statically determinate structure. Now, here you can also see that for this type of portal frame, these all are roller support. So roller support. And I told you in roller support, it can give a reaction only perpendicular to its support. So there will be one, there will be another one, here will be another one. Same is shown here. Okay, like this. Total number of reactions is equal to 3, and total number of equations is equal to 3. So it's again statically determinate structure. And in this type of truss structure, you can also find out whether it's statically determinate and statically indeterminate. So it's statically determinate structure. Let's see some of the few examples in which number of reactions or the number of unknowns is greater than the available equations of motion. That's three equilibrium equations. So for example, we have this continuous beam supported on two roller supports, and from one end it's on a hinge support. This and this one. So we can see that number of reactions it can develop is here it's only one vertical, and here it will be one vertical and one horizontal. Okay, so total number of reactions is sorry, one, two, three, four. So total number of reactions four, and total number of equilibrium equations we can write is only three. So if we compute 4 minus 3 is equal to 1. So IE, this variable is known as degree of statical indeterminacy. So its statical indeterminacy degree is 1. Okay. So we, for example, we can compute three reactions, but there is one reaction in excess of the equilibrium equation. That reaction is known as redundant. Redundant. So we are having one redundant here, and its degree of static indeterminacy is 1. For this fixed beam supported on a roller, now, or we can say it's a propped cantilever. Propped cantilever. We are having three at the fixed support, already mentioned that, and one at this roller support. So its IE will be a degree of indeterminacy will be 4 minus 3, again 1. And in other type of structures, you can see for fixed beam, we have total number of reaction forces is here 3, here 3, 3 plus 3 is equal to 6. So degree of static indeterminacy is 6 minus 3 will be 3. Okay. Degree of static indeterminacy. Then we have a rule. A small sample for this is, for example, total number of unknowns or the total number of reaction forces that are needed to be computed. That is denoted by R. Total number of reactions, okay, R. So if this R value is less than 3, the structure is statically unstable externally. Okay, for example, what happens is we want to see it as I already told you degree of static indeterminacy I is equal to R minus 3. for a 2D structure. 2D structure. So if R is less than 3, we will have IE negative. Okay, that means one equation of motion is in excess of the reaction forces. So that structure will be statically unstable externally. Okay, what I mean by that is, for example, if I remove one support reaction or one support, it will not be stable. It will fall down. If R is exactly equal to 3 in this condition, the structure is statically determinate. As I've told you, for that IE, degree will be R3 minus 3 is equal to 0. For statically determinate structure, degree of indeterminacy I is equal to 0. So it's very simple rule. And if R greater than 3, then structure will be statically indeterminate, because we see that for R greater than 3, IE will come positive. And for all positive cases, there is a degree of indeterminacy. And there will be redundant in our structure, redundant reaction. So it was just a basic about equilibrium of the structure and what are statically determinate and indeterminate structures. You people can look into different problems regarding this. So for today's session, we will go some of the problems, finding the support reactions and other things. So in this problem, I have shown one problem is here. Okay, this one. So in this problem, we have a simply supported beam, but on one side, this this one is on an incline. This hinge is on incline, and this roller is on incline, and it's horizontal from this side. And there is an incline force 12 kilonewton. So please bear with me. So all the units here, FT, consider it to be equal to meter, and K to be equal to kilonewton. Actually, these are American units here used. That's why K equal to kilonewton. Okay, Ft is equal to meter. And if these are the basic things. Okay, just consider these things. So we have a 15, 25. Total is 10 plus 10. 25, 25 meter span beam. And on one side it's like this. There is 6 kilonewton acting at the overhang side and 12 kilonewton acting at a degree 60 degrees to the beam. So one of what are the steps for solving these type of problems is that first and the foremost thing is you have to detach the structure from its supports and draw the free body diagram. That's one of the basic principles in solving problems in structural mechanics. Okay, so here you can see that these structures have been removed, and the supports have been removed, and they have been replaced by reaction forces. So this is a roller support here, and this is a hinge here. From the basics, you can say that it will develop only one reaction here, RA, and it will develop two reactions at support B, BX, and BY. Okay. Now this RA is at some inclination, so this RA will be having. So let me draw it like this. This RA is like this. Okay. So it will be having two components. Uh, RA times in X direction, and another will be in Y direction. RAY. Okay. So we will compute first Rx and Ray. So one more thing we have to keep note of the thing here is that this is a statically determinate structure, because it's a one side it is hinge and another side it is roller. For roller there will be only one reaction developed, and at hinge there will be two reactions developed. 1 plus 2 is equal to 3. Degree of static indeterminacy I is equal to R minus 3. It's actually R. So 3 minus 3 is equal to 0. It's a determinate, okay? Determinate structure. So then we will further, first was the free body diagram. So we are done with free body diagram. We are done with checking the static determinacy. Now we have to compute the support reactions. For support reaction, first we will compute RAX reaction component, X component of reaction A. It will be, so it will be if we its inclination is given there. So it's mentioned in the problem. It's like this, okay? Inclination is given like this, 543, okay? It's a very easy thing. So RAX will be equal to, so if RA is acting like this, so RAX will be equal to RA, it will be cos theta, okay? Theta, okay? And RAY will be equal to, sorry, this is RAY like this. RAY will be equal to RA sine theta. From cos theta and sine theta, you can easily get from this triangle. Cos theta is 3 by 4, 3 by 5 RA, and this is 4 by 5 RA. So this is the basic calculations we did. Then after this, we can choose either of the supports, either A support or B support, and we can use our first equilibrium equation, that is summation of the moments is equal to 0. So let's choose support B. Support B and use summation of MB is equal to 0. Equilibrium equation summation of MB is equal to 0. And using this summation of MB is equal to 0, we can compute RA first. If we use summation of MA is equal to 0, we can compute RB. That's obvious, pretty obvious from the diagram. So for this thing, we have summation MB is equal to 0, and we are taking anti-clockwise direction as positive, okay? Anti-clockwise direction as positive for RA calculation. For RA calculation. So this anti-clockwise is positive. If you will see that this, let's also draw it here. We are having this. We are having RAX like this. We are having RAY like this. Y like this. Okay, we are having 12. We are having 12 kilonewton at 60 degree. We are having, what are the other things? We are having 6 kilonewton. 6 kilonewton. And what are the distances? 10, 10, 5. Okay. This is 10. This is 10. This is 5. Okay. This thing, this thing. Okay. 10 meter, 10 meter, 10 meter. So I already told you this is here, the reaction is this, and we are choosing Bx and Py like this. Here will be Bx and here will be By. So on By we are writing summation of By is equal, summation of Mb is equal to 0. So Ra is passing through, Rax is passing through B, so there will be no moment because of Rax, and Ray is creating a clockwise moment. Okay, so it will create clockwise moment, that's why it is negative. So Ray is equal to minus 4 by 5 here. RAY is equal to 4 by 5 RA, okay? 4 by 5 RA. Then second thing is this 12 kilonewton force. So this 12 kilonewton force is creating a anti-clockwise moment. It will be 12 sine 60 degree, and its lever arm is 10. Here I forgot, here the lever arm is 20. 10 plus 10 up to point B, it's 20. Okay, then we have this 6 kilonewton. 6 kilonewton is causing a clockwise moment here. If you will see at B, it is causing a clockwise moment like this. So it will be negative 6 and lever arm is 5. It will be summation MB is equal 0. When you will compute this thing, RA comes out to be 4.62 kilonewton. Okay, this is the one thing. Then for computing this BX, we can write summation another force equilibrium equation summation Fx is equal to 0, and we will take this as positive. Okay, this direction as positive. Here I will write for RB calculation. Oh, and we know that RAX is equal to 3 by 5 RA, and it is positive because it's acting in the same direction. Okay, this direction, positive direction. RA. Okay, minus. So this 12 kilonewton horizontal component is acting in opposite direction. Minus 12 cos 60 degree. It's very easy seeing from the components plus BX. BX is equal to 0. Putting RA is equal to substituting RA here. We can get BX as 3.23 kilonewton. Okay, and it's in this direction. We computed BX also. Now we are left with BY. So it's clear that for BY we can use upward direction as positive, so that summation of vertical forces Fy is equal to 0. For it's not RB, here I wrote it's BX calculation, for BX calculation. Okay, for BY calculation I can write summation of Fy is equal to 0, and for Fy we are having RAY positive acting this, and RAY is itself is equal to 4 by 5 of RA. Okay, 4 by 5 of RA, and this is acting downwards 12 kilonewton, so it will be minus 12 sine 60 degree. Minus 12, and BY is assumed to be upwards, and minus 6 kilonewton is acting downwards, so minus 6 should be equal to 0. So when we will solve this, we will get our BY as to be equal to 12.7 kilonewton, and it is acting upwards. Okay, so we computed our all things RA, both BX and BY. These are the total number of reactions. So we can have a safety check also whether our calculations are correct or not. For that, we will check calculations. Checking computations. For computations, okay, we can take any of the point and see whether moment equilibrium equation is being satisfied or not. Let's take point C. This is point C. Okay, so we will see whether the summation of all the moments at this point C is equal to 0 or not, because we are having all the support reactions and all the forces with us. So if we will take RA as positive and C summation of moments along at point C is equal to Let's see. First, we will calculate, then we will see whether it is equal to zero or not, because it should be equal to zero as per moment equilibrium equation. So, MC, first it will be minus 4 by 5 of RA, and it is at 25 meters lever arm. Okay. Then it is 12 kilonewton is creating clockwise moment, so 12 sine 60, and it's having 15 meter lever arm. And then we have this RB. Not this BY. BY is creating clockwise moment at point C. Okay, BY. So BY will be equal to BY times it at a distance of 5. Okay. Substituting all the values of RA, RB, and this 4 by 5, RA comes out to be 4.62 multiplied by 25 plus 12 sine 60 degree times 15 minus by came out to be earlier 12.7 and multiplied by 5. If we calculate, this comes out to be 0.01 kilonewton meter. So it's approximately equal to 0. So our summation of MC is coming out to be equal to 0. So our calculations are okay. So if it was not equal to 0, then we have not satisfied moment equilibrium and force equilibrium equations. This is for this problem. Then we are having another beam problem like this. This is a cantilever beam, and on this cantilever beam at a distance of 4 meter, we are having from the fixed end we are having 160 kilonewton load acting, concentrated load acting, and then again at a distance of 8 meter from the fixed support we are having 15 kilonewton per meter UDL acting for a span of 6 meter, and at the free end we are having 400 kilonewton meter this moment acting or couple acting. So first and the foremost thing is detaching the structure from its supports and writing the free body diagram. This is free body diagram. Okay, this is free body diagram. So it's all only having one support, that's the fixed support here. So detaching it from here, we will get this type of thing. So at fixed support, we are having three reaction. First will be axial BX, another will be vertical BY, and there will be one minute MB also generated. Okay. So this is a cantilever beam, and obviously it's a statically determinate structure. Okay. So by applying three equations of equilibrium, we will check first. With the first equation of equilibrium, we will go with this. This is positive along this direction for us, and we are writing summation fx is equal to 0. Okay, summation fx is equal to 0 when we will see that we are having only bx as along acting along x direction, and there is no other load acting along x direction. Bx is equal to 0. We got our first reaction force. Bx is equal to 0 because there was no load acting along the horizontal direction, so there will be no horizontal reaction at the fixed support. Writing our second force equilibrium equation, this will be the positive direction. Loads acting upwards will be considered as positive. Summation of Fy is equal to 0. If we will write this force equilibrium equation, we will be seeing that this 15 kilonewton per meter is acting for a span of, it is opposite, so minus 15 first, it's acting up for a span of 6 meters, so 15 multiplied by 6. Then we have 160 acting downward, so it will be 160 kilonewton. And By is acting upwards, so we will write By. By is acting upwards here. Look. Okay. So we can write this, and this whole is equal to 0. On solving this, we will get By to be equal to 250 kilonewton. And this is sign is coming the same as a geometry, so it will be acting upwards, By. So you need not worry if By came out to be minus 250 kilonewton. kilonewton. So what is the thing behind is that is the assumed direction of the by is opposite. So if it was by is called minus 250 kilonewton, so we assumed it to be acting upwards. You just have to reverse the direction. Then by would have been like 250 acting kilonewton acting downwards. That's the only thing you have to do. Nothing to worry about the sign. Coming sign opposite is just the indication that the assumed direction that you started with is actually the opposite of the actual. And then using the final equilibrium equation, that is summation of. So we are having only one support. We can use on this summation of mb is equal to 0. For that purpose, we will take anti-clockwise moments as positive. If we will take anti-clockwise moments as positive, we will write the equation. So here we have a big 400 kilonewton meter clockwise moment acting at the free end. Okay, acting at the free end. It's a clockwise moment as mentioned. Okay, so it will be taken as minus 400 first. This, then we are having a load of 15 times 6. Okay, first we will convert this 15 kilonewton per meter into load. So it will be 15 kilonewton multiplied by the span 6. Okay, we got this. This is for a span of 6. Then we have to calculate the lever arm. So when we converted it into an equivalent load, so it will then act at the center of gravity of this load. It will act at this point, somewhere this point. So it will be acting. So this like 15 times 6. This is the load. So what is the lever arm? For that we have the lever arm. Total is this is 8 um, and it is 8, 4 plus 4, 8, and for uh, half of 6 is 3. Okay, it will act at a centroid, so it will be and it's creating this 15 into 6 is lever arm 3 plus 8. Okay, then we have 160. It's again creating anti-clockwise moment at this point. So 160 times this thing. So it's creating like this anti-clockwise. So we have plus 160 and its lever arm is 4. Plus MB is again assumed to be anti-clockwise. MB is equal to 0. And when you will do this calculation, you will come up with MB is equal to 1230 minus 1230. You will come up with minus 1230 kilonewton meter. Okay, I already told you if the sign comes out to be negative, then you just have to reverse your assumed direction. So then it was MB minus 1230 kilonewton anti-clockwise like this. So we can write it as MB is equal to positive 1230 kilonewton meter but clockwise. Okay, this is our MB. And checking the computations again for checking computations. For that we can check the summation of the moments at any point and it should be equal to 0. Let's take point A. Okay, point A, we'll check whether the summation of the moments is 0 there or not. We will take summation anti-clockwise MA is equal to 0. When you will write all the moments at that point is, first we have a clockwise 400, so it will be negative 400, and from the others we will have minus 15 first converted to equivalent load, minus 15 multiplied by 6, and it is at a distance of 3. So here this 15 to 6 is only at a distance of 3 from side A, and 160 is at a distance of 4 plus 3 is called 7, and this by, because bx is equal to 0, by is at a distance of 4, 6 plus 4, 10 plus 4, 14. Okay, I'm again writing the same things here. It's creating 160 is creating clockwise, so it will be 160 into 10. Okay, Then we have minus 250 already calculated by, and it's at a distance of 14. And we have this MB, this is clockwise, so it will be again negative as 1230. And when we will calculate this whole thing, this comes out to be equal to 0. It's 250 multiplied by 4 because of 250 this by will create a this by will create an anti-clockwise moment here. By, this is acting upwards, multiplied by this, it will create a anti-clockwise like this here. By is 250, here 250 multiplied by 14. This whole span is 14. So it will be this thing. It will be equal to 0. So our computations are very okay. Everything we have calculated very correctly. So that's why the moment equilibrium equation is being satisfied at any point of beam. Here is another problem. It's a frame type structure. So for this frame type structure, it is being acted by one triangular load. Here again, I will write a consider Ft is equal to meter, K is equal to kilonewton. Yeah, that's the thing. So it is acting for a span of 18 meter, and this is 2.5 kilonewton per meter. Okay, here this, and this is acting for 12 meter, 1.5 kilonewton per meter, and then again for 6 meter again. Here is a concentrated load 15 kilonewton acting midway for this member. So first thing is to check whether this is statically determinate or indeterminate. You people can see that it's a hinge joint here and it's a roller joint here. This hinge joint will be having two reactions, horizontal and vertical. That comes out to be two reactions here, and this roller will give only one vertical reaction, one reaction here. So our R comes out to be equal to 3. So degree of static indeterminacy I is equal to, I already told you, R minus 3, because this is a 2D structure. 3 minus 3 is equal to 0, so it's statically determinate. Statically determinate structure, okay? So we are done with this. Next thing is to draw the free body diagram. Here is the free body diagram. Free body diagram, okay? In the free body diagram, supports are being removed, so we will have two reactions, AY and AX at the in support, and only one reaction at BY at roller support, and all the other loads are shown as it was shown in main structure. So here again we can use only three force equilibrium equations. First, using the first equation is we will use summation of Fx is equal to 0. Okay, we can use it summation Fx is equal to 0, and we are taking these loads acting in this direction to be positive. Okay, so if you will see we are having Ax acting along x direction. Ax, it is assumed to be acting along this direction, so it's positive. Then plus, then we have to convert this triangular load into an equivalent one. We are having a triangular load like this. Okay, so like this, we have to convert it to an equivalent load. So it was 2.5 kilonewton per meter at the end side. Okay, and this is total span is 18 meter. Okay, so what will be the total load acting? Total load acting will be the area under this triangle, 1/2. Load will be L is equal to 1/2. What is its base? 18 meter. What is the load at the altitude? It is 2.5. So your total load will come out to be equal to whatever will be the calculation. We will directly write it here. Okay, so total load is 1 by 2 into 18 into 2.5. Okay, This is the total load acting in x direction, and then we have this 15 kilonewton acting in opposite direction. Okay, 15 kilonewton. So it will be minus 15 is equal to 0. From this, if you perform calculations, AX comes out to be minus 7.5 kilonewton, and the azimuth direction was this. Okay, but since it's negative, so we have to write correct direction for AX to be 7.5 kilonewton along this direction. Okay, we got our first reaction. So this is the first reaction we got. Then we can use moment equilibrium equation as one more thing. This we have to see where this equivalent load will be acting. This will be acting at the centroid of the triangle. It will be like this, and it will be from this point. It will be, centroid from one vertex is, this vertex is 2 by 3 of 18, and it's 1 by 3 of 18. Okay, and this is 1 by 3 of 18 will be 6. This will be acting at a distance of 6. Let me write 1 by 3 of 18 for you people, because this is necessary for moment calculations. We will be requiring it for moment calculations. So we will take our point A. We will write summation of MA is equal to 0. Again, I am using the sign convention. Anti-clockwise moments are positive. Anti-clockwise moments are positive. So if we will see what are the moments being created, so you will see this load L, and this is creating a clockwise moment like this. This is creating a clockwise moment at point A. This point A, okay, point A. This is creating clockwise moment at point A, okay. So what is the total load? It is load is 1 by 2, 18 multiplied by 2.5. And what is the lever arm? It's 6. Okay, 18 divided by 3. 18 by 3. Since it's creating clockwise moment, it will be negative. Okay, then this 15 kilonewton per meter. How we will calculate this? We will calculate first. If you will see, we have to convert this into an equivalent load. This 15 kilonewton will be acting somewhere like this here. Okay, it is total distance is 12 plus 6, 18. So it will be acting at a distance of, perpendicular distance from A point. It will be acting at a distance of 9 meter. Okay, and total will be, this load will be equal to 1.5 multiplied by 18. That's clear. And this is, and if you will see, down, it is creating a moment of, it is creating a clockwise moment at point A. Okay, so it will be again negative 15, 1.5 into 18, and lever arm is 9. I showed you how to calculate this, 9. Then this 15 kilonewton load, what is creating 15 kilonewton load? If you will see, what is the lever arm of this 15 kilonewton load? This 15 kilonewton load is acting at a distance of, this again will be, because this is total 18, this again will be 6. Okay, this will be 6 meter. So it will be acting at a distance of 12 meter, and since it's creating a anti-clockwise moment, so it will be positive. Plus, what is the total load? 15, and what is the lever arm? 12. Okay, 15 plus 15 multiplied by 12. So this by is at a distance of 9 meter from it. So this is 9. And if you check by, what is the by's response here? By's response is again at point A equal to anti-clockwise response. So it will be 9 times by, and everything is equal to 0. When you will perform the calculation, you will get by to be equal to 16.5 positive kilonewton per kilonewton. So azimuth direction is correct. So we got AX by. We have to get AY. AY we will get by using third and the final final force equilibrium equation, that is positive upwards we will take positive, that is vertical forces, summation of vertical forces, summation of Fy is equal to 0. If you will see summation of Fy is equal to 0, Ay is firstly assumed to be acting upwards, Ay is equal to, then there is minus 1.5 kilonewton per meter acting for a span of 18 meter, because it's acting opposite. Look, it is 12 plus 6 is 18, and it's 1.5 kilonewton per meter. So it is acting downward. So it's 1.5 times 18 plus 16.5. This one. AY. Okay. So AY will be, sorry, BY. We have to add plus BY. So BY is 16.5 plus 16.5 is equal to 0. When you will calculate, AY will come out to be 10.5 kilonewton. Okay, it's positive, so it will be acting in upward direction. We calculated all the three things. Similarly, you can, for checking computations, check you can. So it's a very good thing to check whether your calculations are correct or not. So you will take any support or any point in the span. Let's take point C. Okay. So since it's a free and summation of moment should be equal to 0. Let's take summation of MC. Let's calculate summation of MC. Not to take, let's calculate summation of MC. And anti-clockwise to be positive. And if you carefully see all the things, I will write 7.5 times 18, and there will be other forces, right? Do it yourself. It's an exercise for you. Write moments at the point C because of all the forces, and you will see it will come out neatly to be equal to 0. So our calculations are correct. So this I discussed all the problems, beam and the frame problem, and both structures were all the structures were statically determinate structures. So in all the structures, the maximum number of reaction forces to be determined was 3. That's why degree of static and indeterminacy was coming out to be 0. I showed you how to detach the main structure from its supports and then write the support reaction for each support. Knowing that for hinge we have two support reactions, for roller we have one support reaction, and for fixed support we have three support reactions when the structure is considered to be 2D planar structure. And then writing force equilibrium equation, Fx equals 0, Fy is equal to 0. You can get first two unknowns, and then also either starting from any of the force equilibrium equation. That's the moment equilibrium equation, mz equals 0. You will get any of the support reaction. And then I also showed you to check your calculations by taking summation of the moment at any free end or at any support or at any point in the span. And if that comes out to be 0, then your calculations are very correct. Okay. I have one more problem. This arch problem. So it's a hinge support from both sides. You have side A, side B. It's an exercise for you people, and it's having an hinge here. You know, for a hinge, we have one more moment equation there. We can write for one more moment equation, that if it is C, we can write summation MC is equal to 0. Okay, so first detach this structure from supports. You get four reactions: AX, AY. Sorry, it mention it's written here B. Okay, let's also write it B. Summation MB is equal to 0. Okay, CX and CY, you got four reactions. Okay, number R is equal to 4. But if you check IE, it's IE, it is R minus 3 plus some other conditions. Conditions you can write because of this hinges. Because of this hinges, you can write one more condition here, this. So minus is this one. Another force equation condition. So 4 minus 3 plus 1. It is 3 plus 1, so it's coming out to be 0. So this is statically determinate. Determinate structure. So I gave you the hint. This is a free body diagram. Body diagram. This is free body diagram. Take summation Fy is equal to 0. Take this one. Take this one. Summation Fx is equal to 0. And you can take this one also. Summation, sorry, because you can write summation MB is equal to 0. You can get all the four things. Okay. It's an exercise for you. So I think the time is over. It's all for today. So in today's lecture, we discussed some basic definitions regarding the loads. What are the different types of loads? How these loads are being categorized, and what are the how what values we have to take for different loads. Then I gave you a brief introduction about internal stability of the structure, and then statically determinate and statically indeterminate structure. I also told you what are redundants and what is degree of statical indeterminacy. Later on, I had four problems, three beam problems and one hours problem, but because of the time constraint, I solved three brain problems, giving you the full description how to solve those problems. First, remove the supports, draw the free body diagram. First, calculate the degree of statical indeterminacy. Then draw the free body diagram by removing it from supports, and then doing all using force and moment equilibrium conditions. You can get all the reactions. So this problem is an exercise for you people. Thank you everyone for joining. It's all for today.
Thank you, sir. Thank you.